Good morning, everybody. So at the end of the last lecture, we were talking about sets. So we're just going to finish off the set lectures and then talk about maps and interfaces. So a set in Java more or less represents, or is Java's way of representing a mathematical set. Right? So remember, in a set, there are no duplicated elements. So no two elements in a set are equal to one another. You get all of the usual set or mathematical set operations. So in the last class, we looked at the union. Now we're going to look at the intersection and difference. And so an example of a set intersection problem would be if you have a set containing the accounts of students who completed assignment 1 and a second set of students who completed assignment 2, and you would like to know who completed both assignments. And so when you want to, and so in this case, you want to compute the intersection of the two sets. So the set intersection method in Java is called retain all. Right? So the name is a hint to how the algorithm actually works. Right? So S1 retain all S2 tries to keep all of the elements in S2 that are also in S1, right? Or keeps all the elements of S1 that are in S2. Right? And so the method is will transform S1, so it changes S1. So if you don't want to change your original set, you copy the set and then call retain all using the copy. And so here I've got a copied, the copied set's called both assignments, and it's just a copy of S1. And then to compute the set of students who completed both assignments, you just call retain all with the other set. It doesn't change the input set, so it doesn't change S2, right? It changes the set on the left. And so a picture of what happens is the following. There are my students who completed assignment 1. There are the students who completed assignment 2. That's the copy. So that's the copy of S1. So the way retain, the way retain all works is that it iterates over the second set. Right? And so it starts with the first name in S2 and it says it's SP Kuma. So is SP Kuma in both assignments? The answer is yes. So it retains it in both assignments, or it keeps it in both assignments. Right? So is dparrot in both assignments? The answer is yes, it's right there. So it retains dparrot in both assignments. Right? And the last two students are not in this set here, so it doesn't retain them from here. Right? And similarly, it then looks at the remaining elements in both assignments. Right? And it asks, is HP 1304 in this set in S2? The answer is no. Is area 98 in S2? The answer is no. And so you end up with that. All right, and so finally, there's the set difference. So if you have, if you know who completed assignment 1 and who completed assignment 2, and you want to know who completed only assignment 1, that's set 1 minus set 2. And so remove all removes all the elements from S1 that are also in S2. Right? So again, it transforms S1. So if you don't want to change S1, make a copy of it first. So here I have only assignment 1 as my copy of S1. And then I'm going to call remove all on S2, right? Or using S2. Right? So a picture of what that looks like is the following. Students who completed assignment 1, students who completed assignment 2, a copy of S1, right? And now we're going to subtract, we're going to look at what elements are in here and remove them from here, right? And so is SP Kuma in only assignment 1? The answer is yes, so we'll remove it. Right? Is dparrot in this set? Yes, so we'll remove it. Are these two students here? The answer is no, so we don't remove them, right? And we're left with the following two names. Right? And so notice what the union, intersection, and difference methods all have to do. They all have to iterate over some sets, and then they either have to add or remove from a set. Right? And so if your sets were plain old lists, so if they were array lists, and then, so you know how fast it takes to, you know what the complexity of searching a list is. Right? So to search a list, you have to, that takes O(n) time. Right? And so if you have n students in this set, right, and you have another n students in this set, right, if you want to search which students are in both sets, that's an O(n) squared operation, right? You have to iterate over this list, right? And then you have to And then in the inner loop, you have to iterate over the other list, testing who's in this set, right? Do they match a name in this set here? Right? And so the sets in Java, so for these operations, they don't run in n squared time. They all run in O(n) time. O(n) or O(n) log n. Right? But the only way they can do that is if they can efficiently find and remove something from a set. All right, so exactly how the sets are implemented, you'll hopefully learn in SYS 235, your data structures course. All right, so that's all I want to say about sets. Usually you don't get an assignment on these things because there's just not enough time to ask you about everything in the course. There is, however, an older assignment from a previous offering of this course. I'll post a link to that in the announcements on OnQ if you want to see an example of where you might actually want to use these things to solve a computational problem. All right, so the next topic is maps. And so maps are the third, I guess, main data structure that many programmers will use in Java. So a map, most of you will know as a dictionary from Python. And in computing science, these have there's a bunch of different names for what is essentially the same idea. So map, dictionary, and associative array, they're all names for the same data type. Right? And so SYS 235 is one of your courses that is focused mostly on data structures. All right, so if you want to use a map in Java, a map in Java is similar to a map in Java is similar to a Python dictionary. Of course, the way you use it is very different. If you want to think of a dictionary or a map as being a list, right, you can imagine that a map or dictionary is a list where the index is not necessarily an integer value. Right? I guess the other way to think about it is that a list is a map where the index is always, where the key is always an integer. Right? So in Java, you get choices of which maps you'd like to use, just like you get choices of which set or list you want to use. So perhaps in a map or in a dictionary, the key is a set. The keys in your map form a set. And so it's not surprising that the names of the maps have the same prefix as the names of your sets, right? So a hash map uses a hash set to store its keys, right? And a tree map uses a tree set to store its keys. So in Python, in older versions of Python, whenever you used a map, you would the analog in Java would be the hash map. In newer versions of Python, it's actually a linked hash map. So a linked hash map is similar to a linked hash set. It's effectively a hash map that remembers what order you put the keys, the key value pairs into the map in. And so newer versions of Python use something that's similar to a linked hash map. All right, so maps group elements that are accessed by their keys, right? So a list groups elements that are accessed by an integer index. Right? Keys must be unique in a map, right? Which is why it uses a set to represent the keys, right? In a list, all your indexes are unique, right? But that's because they're plain old integers. So every key maps to at most one value, and multiple keys are allowed to map to the same value, right? So the values are not a set, but the keys are. So the values form some kind of collection that's not necessarily a set. And these key value pairs are called entries. So these are the standard terms when talking about maps or associative arrays or dictionaries. But it's much easier to think about these things as just being a table. Right? So let me skip ahead. So there's an example of a map or a dictionary. Right? Your first column is your set of keys, right? So they're unique. Your second column are your set of values. They are not necessarily unique, right? Each row of the table represents an entry into the map, right? And that's it. That's all it really is, right? And so this example here, this is a map of month names to number of days per month, right? February is a bit of a question mark here because sometimes it has 29 days and sometimes it has 28. So notice again that the values are not unique, right? But the keys must be unique. All right, there's lots of other examples of maps in real life. Anywhere you'd want to use a table, you can think of using a map, right? So mathematical one-dimensional functions are maps, right? And often the term map is used in mathematics, right? So for a function, your key is the value x, right? And your value is your y. A dictionary, so an English or a spoken language dictionary, I guess, or written language dictionary, I suppose, would map words to lists of definitions, right? Some words have multiple definitions, and so your values are a list of all the possible definitions, right? We saw the month example here. We can do the same thing with provinces and their capital cities, right? An index in a book is just maps keywords to sets of pages. Student marks in a course you can imagine as storing a map. So actually, for your to keep your maps, I basically build a big to compute your final grades. I basically have a big Excel spreadsheet, and so in the first column of the spreadsheet might be your student number, and then in the remaining columns of the spreadsheet are your marks. Right? You can make it a little more sophisticated than this if you'd like. Right? In the first column, you could have your student number, and then the rest of your marks are stored in a map. So you can have a map of map or a dictionary of dictionaries. Right? And so your map of marks might be assignment 1 and the mark for assignment 1. Right? Then assignment 2 and your mark for assignment 3, and then exam and your mark for the exam, and so on and so on and so forth. Right? So there's no reason you can't build a map of maps. Oh, what just happened? Sorry. Okay. All right, so to make a map, you need, in Java, you need a class that actually implements the map, implements a map. So almost always you pick hash map to begin with because it's very, very fast. So the main operations on a map are you want to get a value from the map, right? So you have a key, you want to know what is the value associated with that key, right? You want to put something into the map, and you want to ask the map, hey, do you have this key already? And so those three operations all have constant time expected complexity for a hash map. Right? So remember how this is true for a hash set as well, right? So in a hash set, you can ask, does the set contain a value? Can I add a value to the set? And can I remove a value from the set? Those have all O1 complexity for a hash set. And just like a hash set, a hash map doesn't keep the rows of the table in any particular order. Right? And performing an operation on the map can change the ordering of the rows. Tree map is normally your second choice. So a tree map is a map that keeps the keys in sorted order, just like a tree set keeps its elements in sorted order. Right? And so not surprisingly, just like a tree set, its main operations have O log n complexity. Right? So fast, but not as fast as a hash map. The advantage, of course, is that the keys are in sorted order. So that so you always know that the set of keys in your map will be sorted. And then finally, you can, if you want to, you can use a linked hash map. So a linked hash map is a hash map that remembers what order you put things into the table. So in other words, the ordering of the rows is always the same. It's almost as fast as a hash map, but it has to remember the ordering, so it takes up more memory. Yes, question? Is it safe to assume that you don't care about the order? So there are applications where you would prefer if the keys were in sorted order. So anything involving strings, for example, where your keys are strings, right? You might want to keep them in sorted order, right? Anything that's yeah. So imagine you have so similarly with a mathematical function, right? You could use a hash map to store the xy value, the xy pairs, right? But if they're not in sorted order, that makes it awkward to do things like plot the function, right? And things like that. Yeah. So there will be applications where you would prefer to use a tree map. Also, if the number of elements you're putting into the map is not enormous, right? So even hundreds of thousands of elements, you really won't notice a big difference between a tree map and a hash map. All right, so just like everything else when you're comparing it to Python, the way you use a Java map is quite different than the way you use a Python map, Python dictionary. Right? Python has a pretty nice syntax for accessing the keys and the values in a map. Java doesn't let you do this, right? So Java doesn't let you replace how the operators work. So it doesn't let you replace how the square brackets work or define how the squiggly brackets work. And so everything in Java has to be a method. So if you want to put something into a map, the method is called put. Right? And so when you put something into a map, basically you're putting an entire row into the map. So you need both the key and the value. And so here I'm going to build a map of capital cities, of provinces and their capital cities. Right? And so because you need to store both the key and the value, you have to tell the map what is the type of the key and what is the type of the value. And they can be different. Right? So for the capital cities and their provinces and their capital cities, both of them are strings. So here I've got a map where the keys are strings and the capital cities are strings. So when you're using a map, you separate the key type and the element type with a comma inside the angled brackets. Yes?
Do tree maps function the same, or do maps function the same as sets do, where you don't have to like put the define into a version of Java, you don't put the definitions after?
On the right-hand side? Yes. So you don't need this on the right-hand side. Yeah. Once you've got your map, you can then start to insert rows into your map. Right? So the method's put, you specify the key, and you specify the value. So Ontario, its capital city is Toronto, and so on and so on and so forth. Right? The only odd one here is St. John's. Right? So for St. John's, you've got the single quote as part of the string name. So if you want to use the single quote as inside of a string, you can't just write the single quote, because the single quote is significant to Java. Right? The single quote indicates the start of a character, start and end of a single character. So if you want to use it as part of a string, you have to tell Java that you don't want the single quote to mean the start or end of a character. Right? So you have to escape it, and that's what the backslash is for. Yes? No, you have to remember in Python strings, you don't care what the delimiter for the string is, right? Single quotes, double quotes, triple quotes all work in Python. Java strings are always double quoted. Yeah. So similarly, if you wanted double quotes inside of a string, you have to escape it. So you need the backslash in front of the character. And so there's many of these there's a few common special characters that you encounter. Right? One of them is the single apostrophe. One of them is the double. One of them is the tab character, so that's \t, and one of them is the new line character. So if you want a string to span 2 lines, you want to insert a new line in the middle of the string. That's \n. Okay, so that map example, this code here builds the following table here. Right? Again, you don't. So this is a tree map. So you do know the order of the keys, right? They are in sorted alphabetic order here. Right? If it were a hash map, they could be, the rows could be jumbled in any sort of order. Okay, so once you've got your map, you can now start to ask your map for information about the rows. Right? So for example, you ask your map of capitals, do you contain the province Ontario? Right? Sorry, what is the capital city for the province of Ontario? Right? And so you use your key, so in this case a province name, and you ask the map to get the value associated with that key. Right? So here your city will be Toronto. Now if the key is not in the map, you end up with the value null, so little null. Right? Null is the value that means no object in Java. So we're not going to run into null for a little while yet. So you don't. So I'm just telling you that so that you know what it means if you encounter it. We'll talk more about null later on in the course. All right. So you can. So there's. So using get, you can ask the map for the capital city of Ontario, right? If you give it a name or if you give it a name that's not in the map, if you give it a key that's not in the map, you get back the value null. So you can also use get to determine whether or not a key is already in the map. Right? You just check the return value to see if it's null. Right? If you'd rather get back a true or false value, use contains key instead. Right? So contains key returns true or false. Right? Does it contain that key there? Right? So here I'm asking the map, do you contain the key Nunavut? Right? And if you do not, so the not is in the front, right? We're going to put Nunavut and its capital city into the map. Right? So we put Iqaluit in with Nunavut, right? And we do the same thing with the other territories. Right? So the Northwest Territories and the Yukon as well. So contains key, true or false, if the key is in the map. All right, so a common introductory problem that's where a map becomes a useful thing to use is when you want to count the number of occurrences of stuff in a collection, right? And you don't want the number of occurrences of a particular thing, but you want the number of occurrences of all of the unique things in a collection of stuff, right? So imagine you have a list of words. So imagine you have a book and you'd like to know how many times does each word occur in this book, right? That is an example, that's a classic example of when you'd want to use a map. Right? So here I'm going to search a list of strings. I want to know how many times each string occurs in the list. And there's lots of reasons why you might want to do this. You might want to know what is the most commonly occurring string, what is the least commonly occurring string, how many times does each string occur on average, and so on and so on and so forth. Right? So the idea here is that you create a map. Your key becomes a word, so a string, right? Where the string will be a word in your list, right? And the value will be the number of times that word appears in the list. So using a map, this is an easy problem to solve. Right? So I'm going to make in this case, a hash map. It doesn't matter what type of map you're going to pick here. I'm using a hash map. So I'm going to make a map of strings, and they're, a map where the string is the key, where strings are the keys and integers are the values. Right? The string will be a word in the list. The integer will be the number of times that word appears in the list. Right? And now you simply iterate over the list. Right? So T is your list here. So for every string S in T, right, you want to ask your map count, right? Do you contain that key? Right? Or do you contain that word? Right? If the answer is yes, right, you want to update the count by 1. Right? So it's very similar to the dice rolling problem that we looked at a couple of lectures ago. Right? Except, so with the dice rolling problem, we could use a list because you know that the value of 2 dice is always an integer value. Right? Here you can't use a list. Well, you can't easily use a list because you're trying to count the number of times each string occurs. Right? So just like in the dice counting problem, I'm going to ask the map how many times does the word currently appear. Right? And so that's going to return back an integer. You can use int here as well. That's fine in this case. Right? Then I'm going to add 1 to that value because I just saw that word again, and I'm going to put it back into the map using the key S. Right? You have to remember here that if the map does not contain that key, then you've now seen the word S for the first time. So if it doesn't contain the key, you want to put in the word S with the count 1 because this is the first time you've seen that word. Right? And if you run that little loop, you'll end up with the number of times each word appears in the list. So when you look at this algorithm here, right, if you have n words in your list, right, you've got a loop here that's going to run n times. Right? So right away you know this has at least complexity big O of n. Right? To compute the actual complexity, you need to know how fast does that method run, what is the complexity of contains key, what is the complexity of get, and what is the complexity of put. Right? If these are all constant time operations, right, they all take a fixed amount of time, then this loop here runs in O(n) time. Right? It's running n times, each operation takes a fixed amount of time, so that becomes proportional to, the amount of time is proportional to n, so it's big O of n. If any one of these operations occurs in more than big O of n, more than constant time, this loop is no longer in O(n). Right? So if you were using a list somehow to keep track of all of the words, right, contains will be on on the size of your list. So right away your list becomes, right away your algorithm becomes on squared. And that similarly, you have to account for how fast does get, what is the complexity of get and what is the complexity of put. Right? And so this is why maps, are useful, right? Especially something like a hash map. All of these operations run in O1 time. Right? And so you know that this loop here should, in most cases, run in On, should have complexity big O of n. Okay, so your keys in your map, they form a set, right? And so if you want to, you can ask the map for its set of keys, right? And so there's a method called keyset that returns the set of keys. Now, keyset doesn't tell you what set, what kind of set it returns, right? It simply says it returns a set. So you don't know if it gives you back a hash set or a tree set, right? You just know it's a set. If you're using a hash map, it's probably returning you back a hash map, a hash set. If you're using a tree map, it's probably returning you back a tree set. But there's no guarantee that that's the case, right? So you shouldn't rely on the fact that it might be a particular set, a particular kind of set. Right? If you're wondering what this thing set is, I'm going to explain that later in this lecture or in the next lecture. Okay, so I'm going to ask for the set of keys. Right? And you know that you can't really do a lot with a set, right? You can ask, does it contain a value? You can put something into the set. You can take something out of the set, right? You can also iterate over a set. So I can write a for each loop over the set, right? And so here, I'm just simply going to print out how many times does each word appear. How many times does each word appear in the list that we built, in the list that we looked at on the previous slide, right? So for each key k, I'm going to get the key from the map of counts, right? And that's going to tell me how many times did the word k appear in that list, right? And then I can print that out here, for example. Similarly, you can iterate over the values of a of a map. Right? So your values in a map, they are not unique, so they form a collection. You might think that it forms a list, but in fact, you don't know that for sure. Right? All that you know is that there's some collection of stuff representing the values in your map. Right? And so if you look at the method values, it tells you it returns this thing called big C collection. Right? You would hope that it would return a big L list, because that would be a lot easier, but it doesn't. It returns a big C collection. Right? And again, we'll see what a collection is shortly, I hope. Once you have your collection, though, you can iterate over it. Right? So it turns out a collection, you can also write a for each loop over a collection. Right? And so here you have a collection of integer, the number of times each word appears. Right? So you can write a for each loop over that collection. Right? And you can sum how many times do all the words appear. Right? So the num strings is going to be my total count of the number of times every word appears. Right? So I'm just going to accumulate the sum into num strings. Right? And if I want to know, on average, how many times does each word appear, you just take num strings and divide it by the size or the number of words, in the number of unique words in the map. Right? And so how do you get the number of unique words in the map? Right? You can ask the key set for its size, or you can ask the map for its size. You can write count.size here too. Right? It's the number of rows in the table. So the size method for a map tells you how many entries are in the map. Right? So that'll tell you the number of times, what is the average number of times each word appears in your list. All right, so key set and values, they don't say what kind of set or what kind of collection are returned by the methods. Right? What you do know, though, is that set begins with a capital S and C begins with a capital C, or collection begins with a capital C. And so you know that for sure, whatever keys is and whatever values is, these things are reference types. Right? So remember, in Java, all reference types begin with a capital letter. And so this thing keys is a reference to a set, and this thing values is a reference to a collection. Right? And in fact, what these are, set and collection, these are things called interfaces. Right? Just like a list is also an interface. Right? So what's an interface? So this is a good place to introduce them. Well, I guess we talked briefly about them when we talked about lists. So in its most common form, an interface is a specification, but not an implementation of what's called an API. So an API is simply a programming interface, right? API, application programming interface. So your interface says what methods must exist, right? And it also says what the methods must do, right? So that's what we mean. So if you ever see the word specification, that's what a software engineer means, right? They're trying to tell you what is the name of the thing and what does that thing do. So an interface in Java is what are the methods this thing has, what do these methods do, right? What the interface doesn't tell you is it does not define how are the methods actually implemented, right? So an interface is really just a list of methods, right, and what the methods do. So there's a list interface, and that tells you what all the methods that every list must provide, right? So every list has a size method, it's got an add method, well, it's got a bunch of add methods, it's got a remove method, and so on and so on and so forth. So what's the difference between an array list and a list? So list is an interface, array list is a class, right? Array list is a class that provides the list interface, right? So that's how things work in Java. Classes are allowed to provide interfaces, can implement interfaces. If a class implements an interface, you know that the class has all the methods that are declared in the interface. So we know that array list has every method that's in list, and it can also add extra methods if it wants to. So interfaces in Java are, in fact, reference types. And that means you can make a variable or a parameter whose type is an interface. Right? So if I have an array list, right, we've been storing array list references in array list variables. You don't have to do that if you don't want to. You can store it in a list variable instead. Right? So on the left-hand side, for the variable type, you are allowed to use an interface name. Right? On the right-hand side, though, you always must pick a class name. Right? So you can say new array list, but you can't say new list. Right? Lists are not objects. Are not classes. They're interfaces. Right? New is only used with classes. So if you want to store something in a list variable, you need to find a class that implements the list interface. Right? And then you need to make an object of that class type. Right? So here I have a new array list. Right? I can store that in a list variable. Here I've got new hash map. I can store that in a map variable. Right? Map is also an interface. All right, so these things, lists, sets, maps, collections, or this thing called collection. These are all part of what Java has named the Java Collection Framework. Right? Basically, it's a bunch of classes, interfaces, and methods. It's called algorithms on this slide that operate on these things called collections. Right? So a collection is just a group of stuff. Right? And so the collection framework has a bunch of interfaces. Right? And so the interfaces define or declare what methods the various types of collections must support. So there's a list interface, there's a set interface, there's a map interface. Right? And there's other interfaces as well. Right? There are classes. So there are different implementations of all the interfaces. Right? So you've got array list and linked list. They both implement the list interface. You've got hash set and tree set that implement the set interface. You've got hash map and tree map that implement the map interface. Right? And then you have a bunch of algorithms, and the algorithms are mostly static methods that operate on collections. Right? And so I briefly mentioned the class called collections with an S, so collections. Right? That class has a bunch of static methods that operate on collections. Right? And so collections in Java are sets and maps. Lists and sets. So there's a way that you can draw this as a picture. You can draw the relationship between all these things using a picture. And so this picture that I'm showing you here is an example of what's called a UML class diagram. UML is short for Unified Modeling Language. We'll come back to this in a week or so. For now, I'm just showing you the picture. So the picture is trying to show you the relationship between the various interfaces in the collection interface. In the collections framework. So at the very top, you've got this thing called collection, right? Remember, that's the type that the values method from map returns. Right? And so you can see here, the collection is marked as an interface, right? And then below it, connected with an arrow, are set, list, and queue. Right? We haven't talked about queue yet, but it's there. Right? We've seen set and list. Right? So what the picture is trying to tell you is that a list is a collection. Right? So in other words, every method that's in collection is also in list. Right? List can add extra methods to its interface if it likes. Right? Set is trying to tell you every method in set is also in collection. And if it wants to, set can add extra methods as well. Right? Sets are different than lists. Right? There's a sorted set and there are unsorted sets. So set is the interface for unsorted sets. Sorted set is the interface for sorted sets. So tree set probably provides the sorted set interface. Right. Okay, so in the red box, these interfaces include all the methods that are defined or declared, up here. Right. And the blue box includes all of the methods from here, which includes all of the methods from here. Right. And so you've got this hierarchy of interfaces. Right. You might ask, where is map? So map forms its own set of interfaces. Right. So map is the topmost interface that describes all maps in Java. Right. And then just like tree set just like you have a sorted set, you also have sorted maps, right, where the keys are in sorted order. So a sorted map includes all of the methods of the map interface. Right. Okay, so what the heck's a collection? Right. So if you go back to the picture, you can kind of guess at what a collection is, right? You know that a list is a collection, and you know that a set is a collection, right? And you remember when I introduced list and set, we saw that a lot of their methods were the same, right? There's an add method in set, there's an add method in list, right? There's contains in set, there's contains in list. There's remove in set, there's remove in list, and so on and so on and so on, right? Why do they have common methods? Because they all have this thing collection in common. Right? So a collection represents a group of objects where every object is called an element. Right? And the collection interface defines the most general operations that you can ask the collection to perform. Right? So if you think about, I've got this group of stuff, what are the most general operations I can perform on this group of stuff? Right? Well, I can ask how many items are in this group of stuff, right? So that's size. Right? I can ask, is this collection empty? Right? Does it contain an object? Right? Can I add something to this collection? Can I remove something from this collection? Right? Notice that size is empty, contains, add, and remove. Those are all in both sets. All of the sets and all of the lists that we saw have these methods. Right? The reason they have these methods is because they all come from this collection interface. Right? There's a bunch of other methods as well. They're not really super important to us right now. So list is a collection, right? That's what this picture is trying to tell you back here, right? List is a collection. So everything in collection is also in list, right? Now lists add extra features, right? Notice what's not in collection, right? There's no method here that takes in an index, right? But lists operate with indexes. So lists add their own methods. Right? So you can access or change an element in a list using an index, right? So we call that positional access, right? You can search a list asking for its numerical position in the list. Right? You can iterate over a list, of course, and you can also perform a bunch of what are called range view operations on a list, right? So in other words, you can do something like get a sublist from a list. And so list adds a bunch of extra methods that take in one or more integer indexes. Right? So notice the syntax at the top. The interface list extends the collection interface. So this keyword extends here is telling you that means that everything in collection is also in list. Right? And now list adds all of this extra stuff as well. Right, so here are all your index-based or all your position-based methods here. Right. What about set? So set is a collection that can't contain duplicate elements. Right? And so how is set implemented? Well, it turns out the set interface only has the methods from collection. Right? And then it adds an extra restriction. Right? The set interface says a set is a collection where no two elements are equal. So it adds a restriction that duplicate elements are prohibited. Right? And finally, there's map. Right? So if you go back and look at collection, right, you should hopefully realize why map can't also be a collection. Right? A collection is a group of items of a single type, right here. But a map isn't. Right? A map is a collection of items or a group of items where everything is a group of rows where every row has two types. Right? And so there's no way that a map can also be a collection. So it forms its own interface. Right? And the map interface says every map has a put, get, and remove operation. Right? It also contains key, contains value, right? And size, and is empty. Right? There's other methods missing from the interface, so this is not complete. Are they here? Oh, they're on the other slide, right? And so you can ask a map for its key set. You can ask the map for its values. You can also ask a map for its rows. So if you want to work with the rows entirely, you can ask for something called the entry set, right? So the entry set, you can think of this as being the rows of the map. Oh, sorry. And so there is your introduction to the Java collection interface, right? There's a bunch of interfaces that define in general what are the operations provided by the various interfaces. Right? The classes, so array list, tree set, hash map, right? Those are classes that implement the interfaces. Right? And you might ask, why are there different classes that implement these interfaces? Why isn't it sufficient just to have one? Right? And so maps and sets is the easiest way to see this. Right? So for maps, you know you have hash map and hash set. Well, sorry, maps and sets, you have hash map and hash set. Right? You know they're very fast. Right? But you also know that they don't keep their elements in sorted order, which is sometimes inconvenient. Right? You can pick a different implementation. If you need the elements in some sort of order, you can use tree set or tree map. Right? But then you pay a price. Right? The price you pay is that their fundamental operations are a little bit slower than hash set and hash map. So the way that the Java language designers created their collections interface is that they provided different classes that they do the same things, right? So all maps do the exact same thing, right? But they are implemented in different ways. And the different implementations have different trade-offs, right? And advantages, right? The programmer can now pick the class that is most suitable for the problem they're trying to solve. Right? And that's very different than the approach that Python took, right? Python, at a superficial level, Python says there's one list, there's one set, there's one map, right? And you're stuck with it. It's not entirely true, but that's the view that you got from SYS 121. Right. All right, and so that wraps up the maps and collections lecture. So I think I'm going to stop there today, because we're going to move on to a different topic next class. I'm pretty sure the next class is when we start to create our own classes. And so that's, we'll do that in the next lecture.